Hope all of you are doing great. My name is Ernest. I'd like to welcome all of us to our channel of Sciences and Mathematics. In our channel, we deal with different aspects of mathematics and sciences. And this is in an effort to try and raise awareness, or rather try to assist one another in trying to improve skills in sciences and mathematics. And this is going to assist us in the long term in trying to find solutions to our ever-changing society. So our main objective is to try and reach as many as possible and try to bring them on board so that we can be able to share this information in this platform and various areas that we're going to find which are basically applicable in our day-to-day life. So I'd like to welcome us. Let's engage in the comment section and also subscribe to our channel so that we can be having updates of our various uploads that we have. So for today, we're going to look at a topic in chemistry. And basically, we have done an introductory part of this aspect of chemistry, which deals with the spatial arrangement of atoms in molecules. And this is the concept of stereochemistry. So today, we're going to look at one of the ways in which we can be able to identify chemicals, especially which fall under this category of the concept of stereochemistry. And we're going to look at ways in which we can be able to quantify, or rather try to look at quantify one of the characteristics of this specific aspect of stereochemistry. And this is the topic of optical activity, and we're going to, of course, further this idea and try to look at ways in which we can be able to relate this aspect of optical activity and chemicals. So without further ado, thank you and welcome. So as I've said, today's topic is basically a branch of stereochemistry, which we said that the concept of stereochemistry deals with the spatial arrangement of atoms in a molecule. And that one, in a sense, of course, gave us a way in which we can be able to appreciate the aspect of stereochemistry, which we said that it finds wide applications in various areas, especially whenever we're trying to talk about the concept of a drug action that we had mentioned. So in us to find a way of describing medical or medicinal drug action, it's good for us to understand the concept of stereochemistry. And later we talked about the concept of organic synthesis, which basically deals with the concept of coming up with various compounds through organic reactions, which are essential in our day-to-day use. And then lastly, we talked about the concept of biomolecules, which of course, in order for us to understand the action of molecules or other biomolecules like enzymes, we have to learn the concept of stereochemistry. So today's topic basically is going to look at one of the experimental ways in which we can be able to identify this characteristic of chemicals, which deals with the concept of stereochemistry. And basically, we're going to look at the concept of optical activity. Now, in order for us to understand the concept of this optical activity, we're going to look at this aspect of optics, but basically this from the physics point of view. I'm going just to be biased on the concept of light. Now, from our topic, of course, on the concept of optical, I want us to understand it from that dimension, that basically that concept deals with the concept of light. And therefore, from this, we're going to see that different aspects or behavior of light is going to be exploited in us trying to identify various chemicals insofar as, or a characteristic of chemicals insofar as stereochemistry is concerned. Therefore, from this aspect of light, we have discussed earlier on in some of our videos in physics that light basically is a form of energy, which is a form of electromagnetic waves. I'm just going to write that one in those specific initials for the sake of a space. So light is a form of electromagnetic waves, which of course can be described using various ways, or we can be able to characterize light in form of electromagnetic waves. And one of the characteristics of light that we have discussed in that particular video on electromagnetic waves is that it possesses energy, just like other forms of electromagnetic waves that we have seen in that range of the EMW spectrum. So therefore, from this, of course, we said that we can be able to describe this particular energy that is contained in the electromagnetic spectrum using the concept of Einstein and Rutherford description of the energy, whereby we had said that energy can be described in form of or rather as a product of the Planck's constant and this is the frequency, and therefore we said further that the frequency can be represented as a ratio between the speed of light and wavelength. So therefore, in us giving just a compounded formula for this energy, therefore we can describe it as a product of these particular two aspects, whereby we're going to see that this frequency is represented as C over lambda. And in this sense, of course, I'm interested in this aspect of lambda and the relationship between this. And therefore, that portrays light as a form of energy which has one of the characteristics of wavelength given as such. So therefore, having mentioned that, therefore, we are going to see that the concept of optical activity is going to rely heavily on this property of light. And therefore, we're going to see that whenever a beam of a monochromatic light, and whenever I'm mentioning the concept of a monochromatic light, now that we've talked about the concept of light, the concept of mono portrays the aspect of a singularity or one. Therefore, this refers, a monochromatic light refers to light of a single wavelength, and therefore, whenever a monochromatic light or a beam of monochromatic light is passed through a polarizer, what we refer to as a polarizer, we're going to see that only light waves oscillating in a single plane passes through the light and is said to be plane polarized. So that's a long statement. Therefore, I'm going just to give that one using an illustration and expound on the concept of this, what we have mentioned as a polarizer. Now, in us discussing the concept of waves and, or rather electromagnetic waves, we say that we can have a different, sorry for that, we can just have an illustrative way of trying to figure out how we can give out the anatomy of a wave. And we say that if we had just a plane, the xy plane, or just a plane in two-dimensional space, which is xy, and then we have this specific point as an origin, we said we can be able to describe a transverse wave giving this particular oscillating particles, which are going to give us this specific output. So in a sense, therefore, we're going to refer to this one as a wave, and we say that a wave has different parts from this specific part to this one. This is a wavelength. From a peak to peak or a trough to trough gives us a wavelength, and therefore we are also going to have different parts, or rather from this specific point to this one, it is referred to as an amplitude. And our main interest is this specific part. So therefore, we are saying that whenever a monochromatic light beam of light is passed through a polarizer, only light waves oscillating in a single plane passes through the slit and is said to be plane polarized. Now, this one is trying to give us an aspect of a plane, and this plane we can be able to describe it as an xy plane that we have already discussed in some of the topics in physics and mathematics. So in an essence, for an electromagnetic wave like light, we're going to see that one of the characteristics of an electromagnetic wave is that it consists of electric and a magnetic wave which are interacting together, and of course they move in an orthogonal, rather right angle, that is insofar as these planes are concerned. So therefore we can be able to illustrate the electric and magnetic waves in this particular aspect, in a sense that before we combine them, we can just have these specific two illustrations. So therefore, if you have, this is the y, x direction, and I can still represent this one as x and y. This is an electric, and this, for the second illustration, we're going to have a magnetic wave for those initials respectively. So if we have an electrical wave that is moving in this specific direction, we are going to include a z or a z plane so that this one can have a three-dimensional representation for that. Therefore, the magnetic wave is going to move in a zx direction. I hope my illustration is going to assist us. So it is going to move in the plane that is going to into the board, while the electric wave is going to move at the plane that is inside the board. So therefore, a combination of these specific two to form an electromagnetic wave is going to give us a product that is going to have an electric wave that is moving in that direction, and a magnetic wave that is moving in that specific direction. My illustration, so right, of course, it's going to be elaborate. So this is a magnetic wave that is moving at a right angle to the first wave that was moving for the electric magnetic. So the combination of the two form an electric magnetic wave, whereby light is part of that category. So having looked at that, therefore that is going to give us a basis of understanding what we refer to as a plane polarized light from that specific aspect of the long statement that we had given. So therefore still we can repeat that statement and say that whenever a beam of monochromatic light, which we have explained, which is a light of a single wavelength, is passed through a polarizer, only light waves oscillating in a single plane passes through the light, and this is referred to as plane polarized. Now therefore, if I'm going to have an illustration of trying to elaborate on that specific statement, let's have a board with a slit at this specific point, and this slit is vertical. Of course, let's assume that this board is aligned cutting into the board, and of course it's perpendicular to the board, and we have a beam of monochromatic light that is incident or just falling on this specific part. And if this beam of light is of course as we have said, is an electromagnetic wave, so we're going to expect it to have the electrical aspect and the magnetic aspect. So therefore the planes of oscillation of electrical and magnetic waves will be at the right angle to one another. So let's assume that it's having this specific aspect for the y and x. One of the oscillating waves is going to be cut in a sense that we're going to have this specific end only an oscillation of a wave which is going to be moving in just a single plane, which is along the board. So therefore the one that is perpendicular, cutting perpendicular to the board, is going to be of course done away with, and that is the aspect of what we call polarization. And therefore we're going to see that in order for us to try and figure out what the concept of polarizing is, this refers to restricting vibrations of an example of a wave like a transverse wave, for instance a light, so that it's able to travel in one direction. And in this sense, we're going to see that for my illustration here, we are going to have a wave that is only traveling in the x and y plane. So that one gives an essence the general illustration, or rather the general illustration of illustrative way in which this statement therefore is describing this aspect of a plane polarized light and the aspect of light as such. So therefore from this we have understood that monochromatic light, whenever it is of course passed through what we refer to as a polarizer. Now this aspect of trying to cut off a specific or restrict specific monochromatic light so that it's able to oscillate just a single plane is referred to as a polarizer. So therefore this particular part that I've given here, which is restricting light in one direction, is what we refer to as a polarizer. Later on we shall look at an illustrative way of trying to represent what I've referred to as a polarizer, after discussing a few concepts which are going to assist us of course understand how that one relates to the optical activities and the aspect of stereochemistry that I mentioned earlier. So we can move on. So therefore we have said that when a beam of a plane polarized light passes through of course when it passes through a polarizer, only light waves oscillating in a single plane passes through the light and is said to be plane polarized. And we're going to expand this one further and see that when a beam of plain polarized light passes through a solution of enantiomers. So we had talked about a polarizer. So therefore, whenever this beam of plain polarized light is passed through a solution of the enantiomers, earlier on we discussed what basically the concept of enantiomers are referred to. So basically I'm not going to elaborate on that, but we had said that for a tetrahedrocarbon that has got a different substitution for X, Y, Z, and W, 4 different substitution, we refer to that one as a chiral center, which is the carbon with a sterical, that specific part. So if we have a plane, or rather a plane at this specific point which represents a mirror image, therefore the reflection of this image at this specific point will give an image of this. May refer to this one as an object. We shall have an image at this specific point, and this is going to give 2 different chemicals with 2 different characteristics, and therefore we're going to refer to either of these chemicals as an enantiomer of the other. So therefore we are going to have this statement that whenever plain polarized light is passed through a solution of enantiomers, sorry for that, the plain polarized light is rotated, hence the molecule is said to be optically active. So whenever a beam of plain polarized light is passed through a solution of enantiomers, the plain polarized light is rotated, and therefore this aspect of rotating this plain polarized light that has been passed through an enantiomer is referred to as, of course these enantiomers are referred to as optically active enantiomers. And therefore we're going to see that this specific behavior by enantiomers whenever exposed to this plain polarized light is going to give us a characteristics of trying to separate the enantiomers from other chemicals, which of course do not fall under this specific category. So this is one of the experimental methods that has been used in order to identify chemicals and different aspects that we're going to see later. But basically for today we're going to look at some of the characteristics of this exposure of light to enantiomers and their behavior. So this concept is known as polarimetric measurements. Just like other scientific methods that we discussed concerning experiments and other aspects which are trying to identify chemicals and their behavior, the concept of polarimetric measurements is carried out in this in an instrument. We're using an instrument known as a polarimeter, and this polarimeter consists of different parts which we're going to give using an illustration shortly, which we're going to give it on the board. Therefore, from our illustration, we're going to see that from the block diagram I've given on the board, this is going to give just different sections which are contained in this polarimeter. And therefore, from this particular point on my left, we have a sodium source which is going to emit what we call an unpolarized light. This means that this light has different characteristics like the planes that we have discussed before and the wavelengths. So therefore we are going to see that at this specific point it's going to pass through the polarizer, which of course is going to give it the aspect of a plain polarized light by allowing or restricting these different aspects of light which is passing through there. So therefore it's going to give this a specific output, as we can see from our demonstration. Let's mention this one and give it as X, Y, and Z oscillation. So therefore we're going to see that the X1 is going to be allowed to pass through, and that aspect is polarization. So therefore at this specific point this light is going to be passed through a sample of an enantiomer, whereby we are going to see that this sample is going to this light is going to be rotated at a specific angle alpha, and the detector is going to of course detect that specific rotation at this particular point. So we're going to have an interface whereby we're going to have the result represented by this section that I've referred to as a printout, whereby we're going to detect the extent of rotation of this specific angle alpha. So therefore, this basically gives the plot diagram for what we call a polarimeter. And therefore, we're going to see that polarimeter, of course, has got these different aspects that I've mentioned. Now, the extent of rotation of a plane polarized light is going to be given by this specific term, alpha rate, alpha nini. This, sorry for that, this Greek term for alpha. And the direction of the rotation is going to be given as either positive or negative alpha, which we are going to demonstrate later. Now, in an essence, we're going to see that optical active molecule or optically active molecules that rotate plane polarized light to the left. Now, in this case, if we try to look at this particular rotation, it's towards the left, and then some enantiomers are going to rotate this specific light towards the right, and we have different terms for that. And we had earlier on said that we can refer this aspect of rotation as either clockwise from this specific point as either clockwise, or this is for clockwise. A rotation to the right is clockwise and this is anti-clockwise respectively. So therefore we can as well refer to the rotation to the right as either clockwise or anti-clockwise. Therefore we are going to have two specific terms that we are going to use in this specific aspect or characteristic of rotation of that plane polarized light by this enantiomer. So the optical active molecules that rotate plane polarized light to the left, which is basically an anti-clockwise direction, we're going to use these specific terms. I'm going to do away with this. I hope it has given us an illustrative way of trying to identify parts of a polarimeter. So therefore, if we talk about this aspect of a rotation of light, this plane polarized light either to the left, we give this one as alpha 1, alpha 2. So therefore, if we describe the rotation towards the right, which is given, or rather to the right is given as we have said, positive, and to the left is given a negative denotation as such. So therefore, whenever we're going to write this alpha followed by negative or positive, then therefore we're going to understand that this refers to the direction of a rotation. Therefore, whenever this rotation is to the left, which is basically anti-clockwise, this is to the left, which is anti-clockwise, we have a specific term that we refer to this specific kind of behavior, and these enantiomers are said to be level rotatory. And whenever it's experience a rotation to the right, which is clockwise, there's a specific term we refer to these enantiomers, and we say that they are said to be dext rotatory. So we have mentioned to say these specific terms whenever we were talking about the concept of configurations, or rather the aspect of a description of chiral centers. And we had mentioned this one in one of our videos, and therefore I'm going to put a link of the playlist of those videos so that we can be able to have a check on them. Now the following signs are used, which are preceding these specific terms that I've mentioned for level rotatory and dext rotatory for these specific rotations. Therefore, we are going to have this one preceding that specific term and this one preceding the second one, respectively. So in our other discussions, we're going to see that this aspect of optical rotation can be able to be specified, and therefore we're going to look at in our next video the concept of a specific rotation. And from there, we're going to have an example whereby we are going to quantify this specific aspect of the angle of rotation, and perhaps that is going to assist us see different behaviors, like maybe the concentration of a specific enantiomer, how it's going to behave with the extent of rotation, and perhaps the aspect of temperatures and the length of maybe the sample holder, etc. So catch us in our next video as we're going to look at another aspect of this optical activity, and that's going to be on the concept of optical mean specific rotation. Now, this particular topics that we have done a discussion for now is going to assist us try to quantify and try to find the rotation, and therefore that, as I've said, is going to assist us as one of the complementary ways of trying to find the concentration, apart from other methods that we have already done in some of our videos. Now, I hope this is going to assist us understand this specific concept and contribute also, or rather complement other discussions that we have had on the concept of stereochemistry, which is going to, of course, compound with others and assist us understand better how we can be able to do experimental analysis of chemicals that fall under this particular category that are optically active. So I hope that is going to assist us, as I've said, and let's catch up in our next video on the concept of a specific rotation. Bye guys, God bless you.